So I asked you about this question, financial diversification. Here, what would be the variance of x plus b, or what would be the risk of the portfolio that invests on both A and B? And given that the variance of A is 36 and variance of B is 8, many of you may have expected something like this, 44, but the actual variance can be calculated directly from this probability distribution table. You have three outcomes with with their respective probability. So if you do the math, so remember how you calculate the variance. First, calculate the mean, and then calculate the deviation, x minus mean, and then square the deviations, and then multiply the probability. So probability weighted square deviations, and then sum them. Sum the squared deviations. Then the answer is 12. 12 is the variance of this portfolio, which is very surprising. So 12 is even smaller than the variance of A. So that is, if you just, for example, if you invest $100 on A, then your risk is 36. But if you additionally invest $100 additional dollars on asset B, then buying another stock will reduce your risk. That's what we just see from this number. And the reason is obvious. The reason is because their covariance is negative. It must be related to the negative relationship between those two assets. Yes, they are. Yes, they are related, and the covariance is the important key component of this analysis. So let's think about, let me then describe what kind of properties you can derive from that observation. First, we will consider adding A and B and make up a new random variable x. By the way, in earlier chapters and like in the last lecture in chapter 3, 4, and 11, when we learned mean, standard deviation, variance, and covariance correlation coefficient, we considered what happens you linearly transform a random variable into another random variable. What we are doing now, it looks similar, but it is very different. It is a kind of linear transformation, but the major difference is that we are considering two random variables at the same time. In our earlier chapters, we have considered only one variable. Transformation of only one variable, simply multiplying, say, 2 and adding another number. Those are fixed numbers, but now what we are adding are random variables. We are adding random variables, so two random variables are merged into a new random variable, one random variable. That's a major difference. Because when you add two things, they may move differently. So there are two randomnesses, so you have to consider how they move together. Therefore, the properties, the formulas may not be simple, but actually it's simple for the mean. The mean formula is pretty simple. There is no difference. Just the mean of the new random variable is simply the sum of the mean of each variable, right? So it is pretty simple, nothing much to say, it's obvious. But the variance is the problem. Variance is not simply addition. So you may have expected variance of A plus B equals variance of A plus variance of B. But here is an additional annoying term coming up here. And it's not simple 2 times, it is 2 times covariance. And I recommend you to think it this way. you may understand variance as a kind of square, right? So variance is basically related to squared deviations. So it involves a process of squaring the number. So you may imagine something like this. X is a plus b. If you take variance of x, that can be thought of as taking square of a plus b, right? And then when you expand it, you can write it as a squared plus b squared plus 2 times cross product. So a squared corresponds to variance of a, b squared corresponds to variance of b, and a times b multiplication corresponds to the covariance, right? And also, in the process of calculating the covariance, we have to multiply two random variables deviations. So it's not totally wrong or weird. It's sensible. It makes sense, makes some sense to understand how this formula is derived. Anyhow, then it's clear. If this covariance is negative, then the new variance can be smaller than the sum. So the more negative this part, then the smaller the final variance will be. And then obviously the standard deviation is simply the square root of this formula, right? So from this, you can study a lot of things. And in our example, back to our example, you may apply the formula to calculate the variance of the portfolio. Because we know everything. The mean of A and B is 10, and the variance of A was 36, variance of B was 8, and covariance between them was minus 16. Then the portfolio, the mean is simple, sum of two expected values. This is pretty straightforward, but the variance part is more complicated. So the variance of the new portfolio is variance of A, which is 36, variance of B, which is 8, and 2 times covariance, which is minus 16. So you get 12 as a result. So this is, and earlier in the previous lecture, I explained as if covariance has no meaning in its magnitude. Though like 16, for example, when the covariance is minus 16, minus sign means that the relationship is negative. But 16 not necessarily means anything, but it is still useful for this manipulation. So when you define a new random variable by combining those two variables, then covariance plays a very important role to determine the variance of the new random variable. So covariance, the magnitude of the covariance is important to calculate the variance. And like from the viewpoint of financial economics, it's clear. Assets having a pair of assets having negative covariance are really useful to diversify the risk. So when you buy an asset, then you should look for another asset that has a negative covariance, right? Have you heard about like long-short strategy? Like if you buy a long position for one asset, then just to hedge the risk, maybe you can buy a short position in a similar asset. So it's a common strategy, even though it's very basic level analysis. Still, it's the basis, the starting point of financial economics. Right? The intuition is clear. And then let's study more about that. Usually, so variance is easily calculated from the covariance, but more in practice, standard deviation is more useful and more commonly used because standard deviation is standardized, but variance is not. Anyhow, then let's think about when can you say like this? when does the standard deviation of the new random variable equals the sum of the two standard deviations? To see when this happens, then so this is the case where you do not have any risk diversification. So simply buying another stock implies buying more risk. This implies variance. By taking square, you will take square in this side and you can write it this way. And this condition is pretty similar to the formula we derived earlier, So it means covariance should equal to standard deviations, multiplication of standard deviations. So when standard deviation times standard deviation equals covariance, then there is no risk diversification. This happens when this happens. So this happens when this happens, and this can be understood as correlation coefficient equals to 1. When the earlier no risk diversification happens, covariance equals standard deviation multiplied, and then automatically the correlation equals to 1 because covariance equals the denominator, right? Therefore, it shows that risk diversification does not occur when correlation coefficient equals to 1. For example, if there are two identical assets, so if I buy one stock of Apple, for example, when I buy Apple, to diversify, I have to buy another stock, right? But if I buy more stocks from Apple, then it does not diversify the risk, right? It's similar to this. If you buy another stock with correlation of 1, then risk does not go away. On the other hand, this is a really powerful result because whenever the correlation is not 1, your standard deviation will be smaller than sum of two standard deviations. There must be some risk diversification whenever correlation is not 1, right? And obviously, perfect correlation does not exist in real world unless you buy the same stock, identical stock, right? So, like always, risk diversification happens all the time, right? It's so easy to materialize. Alternatively, now then, let's study what happens if you have correlation of -1. If you have correlation of -1, which means those two assets are perfectly moving the other way, like ideally moving the other way. When one stock goes up, then the other stock exactly goes down, the same amount or proportional amount, right? In that case, it means the covariance is minus 1 times standard deviations, and then put it back to the formula. You will consider this formula. Variance of x is variance A, variance B plus 2 times covariance. Replace covariance with this relationship, which is implied by covariance -1, and then this equation can be simplified to this squared form, right? Therefore, standard deviation of x equals standard deviation minus standard deviation of b, which is the largest possible risk diversification. Of course, because this is the perfect negative correlation, which is the ideal correlation for risk diversification. And the minimum possible standard deviation you can achieve from a pair of assets is this. So buying another asset B will simply reduce the risk as much as its standard deviation. So it's a perfect risk reduction, risk diversification, right? So this is an interesting, very interesting illustration and consistent with your intuition and what you hear every day. Like diversify your investment and think about the risk, right? That can, of course, all of the analysis are based on statistics, right? So I'm just showing you the very basics of them. Okay, so and one more case. What happens if two random variables are statistically independent? So independence is when two like assets do not affect each other. In that case, independence implies covariance is zero. Correlation, of course, zero. And then in this case, you may think these two assets, two stocks are unrelated, but actually, still you can benefit from your portfolio diversification. So as you can see from this simple inequality, you don't need to prove that. But what I wanted to tell you here is, even if two assets are unrelated to each other, still investing in both of them can reduce your diversification, can reduce your risk. So helps you diversify the risk. So far what I'm saying here is simple statistics and like using variance, covariance, standard deviation, you can study how to minimize the risk. I hope it's interesting to you, and I will make it more realistic and more complicated in the next video. So far it is too simple to analyze. So in the next video, I'm going to consider a more complicated analysis on algebra. So see you later.